Hello again. We're continuing doing problems from section 3.3. So what I wanted to do now was 3.3 number 31. So I'm going to copy the graph from the text. And then we're going to answer each of the questions from it. So, so it comes like this. So it looks like that. Okay, so what they're given here, they say this is y equals f prime of x. So this is a picture of the derivative, not the function, the derivative of the function. We don't have the function. Okay, so I'm sorry, this is, problem 31. So the first part, the graph of the derivative of a continuous function is shown. Okay, they're telling us f is a continuous function. So we've got to assume that it's defined all through here. But notice the derivative isn't defined there. So that means most likely we've got some kind of corner or cusp, some kind of point there where maybe the derivative doesn't exist, or maybe the derivative is a vertical line. The tangent line is a vertical line, so the slope is infinite, so the derivative doesn't exist there. Okay, so let's see what they ask us. A, B, C, D, E. Part A is on what intervals is f increasing and is f decreasing? The original function, not the derivative. The original function. Okay, so what can we get from the derivative to tell us whether the function is increasing or decreasing? It's whether the derivative is positive or negative, right? Because if the derivative is positive, the function's increasing. If it's negative, the function's decreasing. Where is this this is the graph of the derivative. It's positive where the graph is above the x-axis. It's negative where the graph is below the x-axis. So the function is increasing from 0 to 2, and let's see, from 4 to 6, and from, this is 8, from 8 to 9. So those are all the places where the graph of the derivative lies above the x-axis. The other places are where the graph lies below the x-axis. So the function is decreasing where f prime lies below the x-axis, which is 2 to 4 and 6 to 8. So there's our answers. We know where f is decreasing, we know where f is increasing. Okay, let's do B. Now on all of these, what would be really good is for you to stop and do it yourself and then see if you agree with me. On part B, where we want to know where at what x does f have a local maximum or local minimum? Okay, so local max, f local min. Notice we don't know what exactly the value of that local max or local min is, because we don't know anything about the actual values of f. All we're getting is the shape of the graph. So a local maximum would look like that. So it would mean the function would be increasing and then decreasing, which would mean f would be positive, then f prime would be positive, and then negative. So the derivative goes positive to negative here at x equal to 2. Where else does it go positive to negative? Right here at x equal to 6. Okay, where does it go from negative to positive? Well, that would be from negative to positive at x equal to 4. Again, we're looking for a minimum, so we want to go negative to positive. The first derivative is negative to positive. The function is decreasing and then increasing. So negative to positive is there. Negative to positive is there too. So we've got 2 local maxes and 2 local mins. Okay. So now we've got the next question. C is the intervals. On what intervals is it concave up? The original function concave up. What intervals is it concave down? So let's see. Concave up, F concave down. Okay. How do we do that? We've got the derivative. We don't have the second derivative. We don't have the function. But we know that F would, notice one thing, look at our chart. When the second derivative is negative, that means F prime, the first derivative, must be decreasing. When the second derivative is positive, that must be F prime, that must mean F prime is increasing. So the places where the derivative is increasing or decreasing would give us concave up and concave down. Okay, so let's see. The derivative is decreasing from 0 to 3. So the derivative is decreasing from 0 to 3. That must mean F is concave down there. Because if this is decreasing, the second derivative would be negative, so we'd be concave down. From here to here, the derivative is increasing, so the second derivative must be positive, therefore this would be concave up. F would be concave up. Okay, let's see what's happening here. We're going from 6 to 9. The derivative is increasing, so we must be concave up there too. Now that gives me an idea. At this point, we go from a positive derivative to a negative derivative. We jump. So that means our function goes from increasing to decreasing, but we remain concave up. So I already know that right here we're going to have something like this. F is increasing, F is decreasing over here, increasing over here. They're concave up on both sides. So we know what's going on here at this really strange place. What's going on here, we change from concave down to concave up. So this represents an inflection point. At x equal to 3, we're going to have an inflection point. So this was in part D. X equal to 3 is where an inflection point is. What's an inflection point? Where you change from concave down to concave up or concave up to concave down. So notice from 0 to 3 is the only place that the function is concave down. And then from 3 throughout the rest, it's concave up. Okay, so x equal to 3 is the only inflection point. Now what you have to do is take A, B, and C and put it all together to figure out the shape of the graph. So let's see how we can do that. So we already commented on what's going on here at 6. We think our function is looking like that. We already know that. Let's see. Here we go from increasing to decreasing, right? So out here we're going to have something like increasing to decreasing, something like this, right? increasing to decreasing, and we have an inflection point here. So we're going to be going like this. Here's an inflection. Oh, wait a minute. So let me see. Increasing at 2, we're going to hit our local max. And then we're going to be decreasing. And here, concave down. Here we switch from concave down to concave up, right? So we go from concave down to concave up. Okay, so now what's happening here? Here we go from concave down to concave up. Here we hit a minimum. Okay, so I'm going to try to line this up. We hit a minimum here. Here we change concavity. Here we hit a maximum. Let me fix this. And then we're going to go up, and it looks like we're going to hit that, and then come down, and then we go from negative to positive, so we're going from decrease. So it looks like we're going to have something like that. Where are these peaks exactly? I don't know. All we know is the shape. So what you have to do is I would draw the F down here. You don't need a y-axis because we don't know where this is. It could be way up here, could be way down here. We don't know. We have no idea. We do know we can look at all our intervals. What's happening on this interval, this interval, this interval, and we can make a guess and then check and see if it fits and make it a little more symmetric. We don't know how far up to go here, how far down to go here, how far up to go here, how far we don't know. All we know is that that's got to be the shape. So this is what you need to do for those, for 32. Just answer each question in turn and then sketch a possible graph. I'll be back with more.